Welcome to the Deep Dive. We're the show that takes complex science and boils it down to the core ideas you need. Today we're tackling something that honestly might just rewire how you think about electricity itself. We're going to start somewhere really familiar. Think back to basic physics class. Ohm's law. It's, the absolute cornerstone. Voltage equals current times resistance. V equals IR. And for almost 200 years since Georg Ohm figured this out way back in 1827, this straightforward, linear relationship has held up. It's the foundation for pretty much all electronics. Even when things got, let's say, a bit more complicated, like adding magnetic fields, you get magnetoresistance, where resistance changes, or the Hall effect, that voltage popping up sideways. But still, through all that, the core idea that voltage and current were directly linearly proportional, that seemed rock solid, unshakable.
Until now. That's where this story gets really interesting, actually quite revolutionary. Recent experiments, we're talking cutting-edge stuff, are showing that this fundamental law, it breaks down. Not everywhere, mind you, but in a very specific kind of special class of materials.
Whoa, okay, breaks down. Not just a little wiggle, but actually breaks.
Fundamentally, it's a different relationship between voltage and current emerging.
Okay, let's unpack this because that sounds like a pretty big deal. Imagine the basic rules of electricity just changing in certain situations. Like picture sending current one way through a wire, you get a certain voltage. Then you flip the current, send it the exact opposite direction.
Oh.
Normally, you'd expect just the negative of the first voltage, right?
Exactly. That's reciprocity.
But here you're saying you might get something completely different, not just the negative value.
That's precisely it. Something entirely different. And that's what we're diving into today.
We're exploring nonlinear transport in non-centrosymmetric systems. Quite a mouthful, I know. But our mission here is to figure out what these systems are, why their atomic structure makes Ohm's law go. Well, nonlinear. We'll look at the new electrical effects popping up, the really subtle quantum physics behind it all. And maybe the most exciting part, the kind of mind-bending real-world uses emerging from this shift.
Yeah, we'll explore how the material's basic symmetry, or really its lack of symmetry, dictates these new electrical tricks. We'll touch on some pretty exotic quantum ideas, things like the Berry curvature dipole and Berry connection polarizability. Don't worry, we'll break them down. And then we'll see how scientists are actually harnessing these discoveries. Think cutting-edge computing with electron spintronics, or even devices that could pull power right out of the air. Energy harvesting.
It sounds like a journey into the hidden quantum architecture of materials.
It really is, uncovering properties that were there all along, but we just didn't have the tools or the framework to see them.
So get ready for maybe a few aha moments.
Okay.
This deep dive is your shortcut to understanding some genuinely surprising science at the absolute forefront of materials and electronics today. 1. The enduring legacy of Ohm's law and its modern challenge. Okay, so let's start with that foundation we thought was so solid. Ohm's law. Picture Georg Ohm back in 1827. He's doing these incredibly careful experiments, using thermocouples, different wires, different lengths, changing temperatures, meticulous work.
Really systematic.
Exactly, and what he finds, again and again, is this beautifully simple pattern. Voltage and current, they just go hand in hand, directly proportional. Double one, you double the other.
A straight line on a graph. V proportional to I.
And that observation, Ohm's law, VIR, it became the bedrock. It underpins almost everything electrical we've built since. Microchips, power grids, you name it.
What's truly remarkable, though, is how long that simple linear relationship held up, even as physics got way more complex. Think about William Thomson, Lord Kelvin, in 1857. He finds that a magnetic field can actually change a material's resistance. That's magnetoresistance.
Right, still useful today.
Absolutely. And then Edwin Hall in 1879 discovers something maybe even weirder. Pass current through a conductor, put it in a magnetic field, and boom, a voltage appears sideways, perpendicular to both. The Hall effect.
Another cornerstone used in sensors everywhere.
Precisely. But even with these effects, the relationship between the voltage and the current flowing through the material stayed linear. Sure, we needed a more complicated equation to describe everything. You could write it like V equals, say, R10 times I. That's the basic ohmic part. Plus, maybe another term for magnetoresistance, like R12 times I times B squared. And another for the Hall effect, maybe R11 times I times B.
Okay, so more terms, but I see each term still has a voltage proportional to just I, the current.
Exactly. Even when we applied a magnetic field, which breaks something called time reversal symmetry, basically, the physics looks different if you run time backwards. The linearity with current held firm.
So for almost 2 centuries, this linear world was just how electricity worked. Full stop. But now, Things are changing. You said recent experiments are showing this profound breakdown, not just bending the rules, but breaking them, particularly in these non-centrosymmetric structures. What does that actually mean?
Right. So, non-centrosymmetric. It sounds technical, but the core idea is about symmetry. Specifically, a type of symmetry called inversion symmetry. Physicists often denote it as P. Think about reflecting a system through its center point. Every coordinate, xyz, goes to xyz. If the system looks exactly the same after you do that, it has inversion symmetry. It's centrosymmetric.
Like a perfect sphere or a cube, flip it through the middle, looks the same.
Exactly. But if it doesn't look the same, if going one way is fundamentally different from going the opposite way, then it lacks inversion symmetry. It's non-centrosymmetric.
Okay, give me an analogy.
Think of a perfectly symmetrical snowflake. Center symmetric. Now think of a spiral staircase.
Ah, right. If you reflect that through its center, a right-handed spiral becomes a left-handed one. It's different.
Precisely. That handedness, that inherent directionality is the key. In these non-centrosymmetric materials, inversion symmetry is broken. And what that means for electrons moving inside is profound. Moving forward isn't the same as moving backward. They might experience different resistance, different forces.
So the path isn't symmetrical.
Correct. And that asymmetry is what unlocks the door to these nonlinear transport effects. Instead of just V proportional to I, you start seeing V proportional to I squared. Or even higher powers. The linear rule breaks down. And to really stress how weird this is, this second-order effect is often called non-reciprocal. Think of a classic diode in electronics. It lets current flow easily one way but blocks it the other. V plus I is very different from VEI.
It's a one-way street for current.
These non-centrosymmetric materials can behave somewhat like that intrinsically. V plus I is not equal to VI. This is really different from other nonlinear things you might encounter, like, say, tunnel junctions. They can be nonlinear, yes, but they're still usually reciprocal. Reverse the current, you get the negative voltage.
But here, the reciprocity itself is broken. Flip the current, and you get a genuinely different voltage magnitude or behavior, not just the mirror image.
Exactly. It's a fundamental shift in the material's response.
Wow. That really is a game changer. It suggests you could build directionality right into the fabric of the material itself. 2. Decoding non-centrosymmetric systems. A matter of symmetry.
So, digging deeper into this symmetry idea, inversion symmetry. P, we said if a system looks the same when you map XYZ to XYZ, it's centrosymmetric. If not, it's non-centrosymmetric.
Like the snowflake versus the spiral staircase.
Yeah.
Got it. One direction isn't equivalent to the opposite.
Precisely. And that breaking of inversion symmetry, P, isn't just incidental. It is the absolute requirement for these second-order nonlinear effects to even exist. Physics dictates that in any material belonging to a centrosymmetric point group, that's the mathematical classification of its crystal symmetry, these second-order effects are strictly forbidden. 0.
So symmetry actually forbids it.
Yes. It's only when P is broken that the door opens. And then the specific way the nonlinearity shows up, like, does the voltage appear along the current or sideways? How does it depend on a magnetic field? That depends on what other symmetries might still be present or broken in the crystal.
It's like the overall blueprint of the crystal dictates the exact rules of this new nonlinear game.
Perfectly put. Now, within this nonlinear world, we generally talk about two main flavors of effects. It helps to distinguish them based on whether a magnetic field is involved. First, there's nonlinear magnetoconductivity, or NLMC. As the name implies, this happens when you have both nonlinearity and an external magnetic field, B. Typically, you apply an AC current, say at frequency omega, and you look for a voltage response at double the frequency, 2O. For NLMC, this V2O sails quadratically with the input current, so IO2, and linearly with the magnetic field, B.
So V is proportional to I squared times B.
Exactly. This was actually first noticed, though maybe not fully understood in this context, quite a while ago in chiral crystals, those handed ones we mentioned. It was called electrical magnetochral anisotropy. But now we see it in lots of places. Polar semiconductors, topological insulators, 2D electron gases.
Right, and you mentioned the terminology can be a bit of a mess here. People call it different things.
Oh, definitely. You'll see papers talking about bilinear magnetoelectric resistance, bilinear magnetoresistance, unidirectional magnetoresistance. It can get confusing fast.
Yeah.
So to try and bring some clarity, we strongly suggest using NLMC as the umbrella term. It just means any V2 that goes like I squared times B, regardless of whether you measure the voltage along the current or sideways, or what specific material it is. Standardization really helps a field like this move forward.
Makes sense. Okay, so that's NLMC needs a magnetic field. What's the other type?
The other main category is nonlinear conductivity, or NLC. This is the nonlinearity you can get without any external magnetic field at all, 0B field. Here, the second harmonic voltage, V2, scales purely quadratically with the current.
Just like you.
So V proportional just to I squared.
Correct. And probably the most famous and arguably most surprising example of NLC is the nonlinear Hall effect, the NLHE. This is where you get that transverse voltage perpendicular to current again with no magnetic field applied. That's the really mind-bending one, right? Getting a Hall effect without the Hall, without the magnet.
It really is, because the standard Hall effect absolutely needs that B field to break time reversal symmetry, T. But the NLHE can happen in systems where inversion symmetry, P, is broken, but time reversal symmetry, T, is actually still intact.
How is that even possible?
It turns out that Onsager's reciprocity relations, these fundamental rules that govern linear responses in physics, they just don't apply in the same way in the nonlinear regime. The rulebook changes when you go nonlinear.
So breaking inversion symmetry is enough to get this sideways voltage, even if time symmetry holds. Wild.
It is pretty wild. And again, nomenclature needs care. People sometimes call any transverse nonlinear voltage a nonlinear Hall effect. But strictly speaking, Hall should imply a non-dissipative response, meaning no energy lost as heat, like in the quantum Hall effect. So we suggest using NLC as the broad term for all zero field effects. Then you can specify longitudinal NLC if the voltage is along the current, or transverse NLC if it's sideways. And reserve NLHE specifically for those transverse NLC signals that are proven to be non-dissipative, arising from things like Berry curvature, which we'll get to.
Okay, clarity is key. NLC for zero field, NLMC with a field. Got it.
Now, the beauty here is the predictive power. As we hinted, the material's crystal symmetry, its point group, tells you exactly what kind of nonlinear response to expect. Theoretically, we describe this using tensors. For NLC, the second-order current density, the J2, is related to the first-order electric field by the NLC tensor, often written as 2. These tensors basically encode all the directional information. And crucially, the allowed components of this tensor for every crystal symmetry are known. They're tabulated in databases like the Bilbao crystallographic server.
So you can literally look up a material symmetry and see what nonlinear effects are allowed.
Essentially, yes. Experimentally, we usually measure resistivity instead of conductivity, but there are straightforward ways to convert between them. The same logic applies to NLMC. There's an NLMC tensor that connects the nonlinear current to both the electric field and the magnetic field. While these specific NLMC tensors might not be listed directly in all databases yet, the methods to generate them from symmetry principles exist.
That's incredible. So symmetry isn't just descriptive, it's prescriptive. It's a design tool. You can predict, okay, this crystal structure should give me a transverse NLC signal, but no longitudinal one. And then you go test it.
Exactly. And it's a vital sanity check. Researchers consult these symmetry tables. If they measure a nonlinear signal that shouldn't be there according to the material's symmetry, that's a huge red flag.
Meaning?
Meaning maybe the signal isn't intrinsic to the bulk material. Maybe it's coming from the surface, or it's a thermal effect masquerading as nonlinearity, or some other experimental artifact.
Right, so symmetry analysis keeps the experiments honest.
Absolutely critical for reliable science in this field. 3, where the action happens. Experimental discoveries across diverse materials.
Okay, so we have the theory, the symmetry rules.
Yeah.
Where are people actually seeing these effects? Let's talk materials.
Great. Let's start with polar systems. These materials have an inherent directionality built into their crystal structure, like a tiny electric dipole moment per unit cell. They often have spontaneous electric polarization.
Like tiny internal compass needles, but electric ones.
Kind of, yeah. And a really key example here, one that made big waves, is tungsten ditelluride, WT2.
Right, you mentioned this one earlier. What was the big deal there?
Researchers saw a really clear transverse NLC signal, that nonlinear Hall effect in WT2. And crucially, they could directly link it to an intrinsic quantum mechanism called the Berry curvature dipole, or BCD. We'll definitely unpack BCD later, but think of it as a measure of the twistiness in the electron's quantum behavior.
And the significance was?
It was a slam dunk demonstration of a Hall-like effect happening without breaking time reversal symmetry. Just breaking inversion symmetry was enough, powered by this BCD. Plus, they showed you could use this NLC signal to actually detect the direction of the material's internal electric polarization, even flip the polarization and see the NLC signal respond ferroelectric control.
Wow, so you can electrically write and read this nonlinear state. That smells like memory applications.
Potentially, yes. Similar NLC effects driven by BCD have been seen in related materials like molybdenum ditelluride, MOTI2, and also in things like NBrP4. Although it's important to say in some other polar materials like Bikebrev or BonSB2, it looks like extrinsic effects, things related to how electrons scatter off imperfections, play a bigger role than the intrinsic BCD. So the details matter.
So it's not always the same mechanism even in similar materials.
Right. And NLMC, the magnetic field version, was also seen in WT2 and Bikebrev, both along the current and sideways. A key finding there was that the NLMC signal popped up when the magnetic field was perpendicular to the voltage measurement direction. This specific geometry ties into the material having a helical spin texture, electron spins winding around like a helix.
Okay, interesting. Polar systems. What's next?
Let's talk chiral systems. Chiral means handed, like your left and right hands. They're mirror images, but you can't superimpose them. These materials lack any symmetry operation that flips orientation, like a mirror plane or inversion center.
And the classic example is elemental tellurium.
Exactly. Tellurium atoms naturally form these little helical chains, like atomic corkscrews. So the whole crystal has a definite handedness. You can have right-handed or left-handed tellurium crystals. It's also a decent semiconductor, which helps for experiments.
And did they see nonlinear effects there?
Yes. NLMC was first hinted at in artificial bismuth helices years ago, but seeing it clearly in actual tellurium crystals was a big step. There were some early puzzles where the signal didn't perfectly match the expected symmetry, which actually taught the field a valuable lesson about being careful with experimental artifacts.
Ah, the symmetry check again.
Right. But later studies on thin flakes of tellurium beautifully confirmed the theory. They even showed they could tune the NLMC signal with an electric gate, and crucially, the signal had the opposite sign in right-handed versus left-handed flakes.
That's direct proof it's linked to the chirality.
Unmistakable proof. And interestingly, unlike the polar systems, in chiral tellurium, the NLMC signal is strongest when the magnetic field is parallel to the voltage direction. This points to a different kind of spin pattern, a radial spin texture. They've also seen longitudinal NLC in tellurium, adding to its unique nonlinear fingerprint.
Fascinating. Okay, polar, chiral, what else?
A really important area is surfaces and interfaces. Here's the insight. Even if a material is perfectly centrosymmetric in its bulk, its surface inherently breaks inversion symmetry.
Ah, because there's material on one side and vacuum or air on the other. No symmetry across the boundary.
Exactly. So nonlinear effects can pop up just at the surface, even in boring bulk materials. This is super relevant for systems where transport happens mainly at the surface, like 2D electron gases, 2D EGs, or topological insulators.
Right. TIs have those special surface states where electrons can zip around.
Precisely. And NLMC has been widely seen in both 2DEGs and TIs. Often these systems have helical spin textures at the surface, similar to the polar materials, leading to NLMC when the B field is in the plane but perpendicular to the current. If you break more surface symmetries, you can even get NLMC with an out-of-plane B field. And critically, you can often use gating to control how much the surface contributes versus the bulk. This gives you a knob to tune the NLMC signal, which is great for potential devices.
So you can electrically control the surface nonlinearity.
Yes. And NLC, the zero-field version, has also been found in these systems, sometimes even surviving up to room temperature. That's a big plus for practicality. People have even shown non-volatile switching of the NLC signal in materials like PBSNT, suggesting memory applications again. Room temperature NLC was even seen on the surface of plain old bismuth, which is easy to work with and compatible with standard chip technology, CMOS. And you can boost the signal by shaping the device, like making it arc-shaped.
So surfaces offer a whole playground for finding and engineering these effects.
Definitely. Which leads us naturally to engineered structures. Since many common crystals are centrosymmetric, sometimes the easiest way to get nonlinearity is to build it yourself.
Like atomic scale construction.
Pretty much.
Yeah.
Van der Waals materials are perfect for this. These are layered materials like graphene, boron nitride, TMDCs. You can peel them down to single atomic layers. Then you can stack them in specific sequences, stretch them, twist them relative to each other. You can intentionally break symmetries.
This is the twistronics and heterostructure engineering stuff.
Exactly. Take graphene. A single sheet is centrosymmetric. No second-order nonlinearity, but sandwich it between layers of hexagonal boron nitride, HBN, which has a different structure, and boom, you break inversion symmetry for the graphene. Suddenly, you get both longitudinal and transverse NLC in that HBN graphene BN stack.
Just by layering them.
just by layering. Or even more dramatically, just twist two layers of graphene slightly relative to each other, twisted bilayer graphene. This creates entirely new electronic states and can lead to huge NLC signals. Even just artificially wrinkling bilayer graphene can induce NLC.
Wow. So tiny structural changes have massive electrical consequence.
Absolutely. People have seen large NLC in stretched or twisted WSE2 and shown ferroelectric control in heterostructures of WSE-WT2. It's a really powerful way to design nonlinear responses.
Okay, one more category you mentioned, magnetic systems.
Right. So here we have materials that are both non-centrosymmetric, P is broken, and magnetic, time reversal symmetry, T is also broken. In these materials, the nonlinearity can be influenced not just by external fields, but by the material's own internal magnetism, its magnetization M in ferromagnets, or its Neal vector N in antiferromagnets.
So the internal magnets act like tiny built-in B fields affecting the nonlinear response.
In a sense, yes. They provide additional symmetry-breaking fields. A fascinating example is MnB2T4. It's a topological insulator. If you have an odd number of layers, it's ferromagnetic. It shows a nonlinear voltage whose sign you can flip just by reversing the overall magnetization direction. Great for reading magnetic state.
Electrical readout of magnetism.
Yes. Now, if you have an even number of layers, it becomes an antiferromagnet. Here, both P and T are broken, but a combined symmetry, PT, is preserved. This PT symmetry actually suppresses some common nonlinear mechanisms like the BCD. Instead, something else, likely the Berry connection polarizability, BCP, takes over. And remarkably, you can modulate the nonlinear signal just by flipping the Neal vector the direction of the staggered magnetic spins.
Flipping the antiferromagnetic order changes the electrical output.
Correct. Similar control has been shown in other antiferromagnets like Cumdays using current pulses and MM3SN using small fields. And the van der Waals magnet CRSBR shows anomalous NLMC you can control with both M and N.
So the big takeaway here for listeners.
It means these nonlinear effects, particularly anomalous NLMC, give us a new, purely electrical way to read the state of both ferromagnets and, importantly, antiferromagnets. That's huge for future magnetic memory and computing.
And one last point. You mentioned even centrosymmetric materials can join the party.
Right. Sometimes a material that's normally symmetric can undergo a phase transition driven by temperature, pressure, field, whatever that breaks inversion symmetry. When that happens, nonlinear transport effects can suddenly switch on. So measuring these nonlinear signals can be a super-sensitive probe to detect and study the phase transitions themselves. 4. The driving forces. Microscopic mechanisms behind the magic.
Okay, this is fascinating. We see these effects in all sorts of materials, but why? What's happening at the quantum level? Let's get into the mechanisms.
Right. Let's start with nonlinear conductivity, NLC. The zero field case, especially the nonlinear Hall effect. The star player here is often the Berry curvature dipole, BCD.
Okay, Berry curvature again. You said it's like a quantum twistiness?
Yeah, think of it as an effective magnetic field that electrons feel in momentum space, arising purely from the material's quantum mechanical band structure. Normally, in systems with time reversal symmetry, the Berry curvature at a momentum point k is exactly the opposite of the curvature at k. So if you sum over all occupied electron states, it averages to 0. No net effect.
Yeah, cancels out.
But when you apply an electric field in a non-centrosymmetric material, you drive the electrons out of equilibrium. The states K and K are no longer occupied equally. There's an imbalance. Because of this imbalance, the Berry curvature doesn't cancel anymore. Specifically, the gradient of the Berry curvature, integrated over the occupied states, can become non-zero. That non-zero integral is the Berry curvature dipole.
So it's like the electric field reveals this underlying imbalance in the quantum twistiness.
That's a great way to put it. The BCD is an intrinsic property baked into the material's band structure that gets activated by the electric field imbalance. And crucially, this BCD mechanism typically leads to a non-dissipative Hall. Current energy isn't lost as heat.
The free lunch hall effect.
In a manner of speaking. And we saw in WT2 and MOT2, this BCD can be really large near topological phase transitions and even change sign, which is interesting for devices. Although it's not always perfectly independent of scattering, impurities can still play a subtle role.
Okay, so BCD is a key intrinsic mechanism for NLC. Are there others?
Yes, there are also extrinsic mechanisms, which have more to do with how electrons scatter off impurities or defects. Think of skew scattering. An electron hits an impurity, and because the system lacks inversion symmetry, it's more likely to scatter off to, say, the left than the right. This asymmetry builds up into a net sideways current.
Like a biased pinball machine.
Kind of. Then there's side jump. When an electron scatters, its position actually shifts slightly sideways during the scattering event itself. This also contributes to a transverse current. Now, the important difference, while BCD typically only gives you a transverse Hall signal, these extrinsic mechanisms can contribute to both transverse NLC and longitudinal NLC nonlinearity along the direction of current. And they are usually dissipative.
So experimentally, how do you tell them apart?
It's tricky. You need to carefully measure the signal's dependence on crystal direction, temperature, maybe sample quality. There are theoretical scaling laws that predict how each mechanism should behave, which helps disentangle them.
Okay, detective work. Now, what about NLMC mechanisms when the magnetic field is on?
For NLMC, microscopic theories point to intrinsic contributions from both Berry curvature effects, related to BCD but now influenced by B, and Zeeman coupling. Zeeman coupling is the interaction of the electron's spin and orbital magnetic moments with the external B field. Both these intrinsic terms often scale quadratically with scattering time, meaning cleaner samples show stronger effects. And the Zeeman part lets you probe spin versus orbital contributions.
So NLMC can be a tool to dissect those internal magnetic properties.
It can. Another really important intrinsic mechanism is the Berry connection polarizability, BCP. Think of it like this. NLMC is like NLC, but perturbed by the magnetic field. The BCP describes how the electron's Berry connection, related to the Berry phase, gets modified by the electric field. This B-field perturbed BCP is thought to contribute an NLMC signal that's independent of scattering time and purely transverse, Hall-like, though there's still some active debate on the exact details.
Quantum geometry gets complicated fast.
It does. And again, extrinsic scattering mechanisms are also important for NLMC, especially in magnetic materials where internal magnetism complicates things further. Similar scaling laws are used to try and identify the dominant players experimentally, as was done in tellurium.
Okay, and finally, that really weird case, anomalous nonlinear magnetoconductivity.
Right. This is for those special magnetic materials that break both P and T, but preserve the combined PT symmetry, like the even layer MnB2T4.
And PT symmetry suppresses many of the usual suspects.
Exactly. It forbids the BCD, standard skew scattering, standard side jump. So where does the nonlinearity come from?
Good question.
Well, the BCP mechanism can still contribute here, even without an external B field in some interpretations. It's thought to be independent and can contribute to both transverse and longitudinal signals. Also, a nonlinear Drude term emerges. This comes from an asymmetry, skewness, in how electron energy depends on momentum. It scales like 2 and has specific symmetry properties, T-odd. PT even. It's actually closely related to the Zeeman term in regular NLMC.
So new terms pop up when PT is preserved.
Yes. And even though standard extrinsic mechanisms are forbidden, a special kind of anomalous skew scattering might still be possible, where Berry curvature and scattering work together in a PT-symmetric way. Untangling all these contributions requires even more careful analysis of scaling laws and symmetry arguments. It's a very active research frontier. We've been deep in the quantum weeds. Let's zoom back out. What can we actually do with all this weird nonlinear stuff? What are the applications? 2 areas really stand out right now. First, spintronics and orbitronics. These fields want to use electron spin and orbital angular momentum, not just charge, for future electronics. The dream is much lower power consumption, faster devices.
Using more of the electron's property.
Exactly. But you need ways to create, control, and detect spin and orbital currents, and that's where non-centrosymmetric materials shine. Remember how breaking inversion symmetry leads to spin orbit or orbital orbit coupling? This creates those spin textures or orbital textures patterns of angular momentum in the material. Now, Edelstein predicted way back in 1990 that if you pass a current through such material, these textures force the electrons to align their spins or orbitals, creating a net internal magnetization or polarization, a current-induced internal field.
The current itself generates a magnetic-like effect inside the material.
Precisely due to the broken symmetry in textures. And NLMC is the perfect tool to see this. If you apply an external B field, it will interact with this internal current-induced field. The resistance will be slightly different depending on whether the external field helps or hinders the internal one. This means measuring NLMC, that difference in resistance for opposite current directions in a B field, gives you a direct, purely electrical way to detect these spin or orbital textures.
So NLMC acts like a probe for these hidden quantum textures.
Exactly. It's been used to confirm helical spin textures in TIs and 2DEGs and radial textures in chiral tellurium. By combining symmetry predictions with NLMC measurements, researchers can design materials with specific textures for things like spin-orbit torque devices used in advanced magnetic memory, MRAM, or novel magnetoelectric sensors.
It's enabling the design of next-gen low-power electronics. Very cool. What's the second big area?
Energy harvesting. This is potentially huge. Think about all the radio frequency RF signals filling the air, Wi-Fi, mobile signals, TV broadcasts.
It's everywhere, an untapped energy source.
Potentially, yes. Especially for powering the billions of tiny Internet of Things, IoT devices, sensors, maybe even medical implants. The idea is to use rectennas, rectifying antennas, to capture this RS energy and convert it into usable DC power.
Self-powered devices, no batteries needed, the dream.
It is. But traditional rectennas have a problem. They use Schottky diodes for the AC to DC conversion. And Schottky diodes have this thermal voltage limitation. They need a minimum input signal strength to work efficiently.
Too weak a signal, and they don't rectify well.
Exactly. So traditional rectennas need a bulky antenna part just to boost the weak ambient signals up to that threshold. This limits miniaturization.
So you can't make them tiny enough for, say, implants or dust-sized sensors.
Right. But here's where the non-centrosymmetric materials come in. Their nonlinear transport is intrinsic. When an RF wave, which is AC, hits the material's own nonlinear response generates an asymmetric internal field, which naturally results in a net DC current. Rectification happens right in the material.
Without needing a separate diode.
Without needing a separate diode. And crucially, this intrinsic mechanism is not bound by the same thermal voltage limitation as Schottky diodes. It can work with much weaker signals.
So you could potentially ditch the bulky booster antenna, make the rectenna much, much smaller.
That's the promise. Microscale, even nanoscale rectennas become feasible. Imagine self-powered sensors woven into clothing or tiny medical monitors powered by ambient Wi-Fi. And we're seeing proofs of concept. TRT4 showed wireless rectification at room temp using its NLC. Chiral tellurium did it too. Bi2T3 has shown rectification up to nearly 30 gigahertz right in the 5G bands.
Wow. Are they as efficient as traditional ones yet?
Not quite yet. Efficiency is still a challenge being worked on, but the principle is demonstrated. It opens a path to fundamentally different, potentially microscopic, wireless power sources. Outro.
So let's try to wrap this up. We started with good old Ohm's law, the simple linear rule that powered electronics for ages. And we found that in these special non-centrosymmetric materials, that rule fundamentally breaks down. Electricity starts playing by new nonlinear rules.
Yeah, we learned it's all about symmetry. Or the lack of it. Whether it's a natural crystal or something carefully engineered, breaking inversion symmetry unlocks these effects: nonlinear conductivity, NLC, and nonlinear magnetoconductivity, NLMC. And these are driven by some deep quantum phenomena like Berry curvature dipoles and connection polarizability, the intricate geometry of electron wave functions.
And it's not just physics theory. These effects have direct lines to potential applications that could genuinely change things. Designing new kinds of magnetic memory, creating tools to see hidden quantum properties like spin textures, and this incredible prospect of wireless energy harvesting to power tiny devices.
It really is a field buzzing with potential right now.
It makes you wonder, if we can now engineer materials atom by atom to break specific symmetries and get these kinds of profound changes in electrical behavior, what's next?
Exactly. What other fundamental physical laws might have loopholes we can exploit if we just break the right symmetries? Could this deep dive into quantum geometry lead to entirely new ways of computing, things beyond the silicon transistors we rely on today? It's a fascinating question to ponder.
It definitely is. The journey from figuring out the basic rules to building revolutionary tech is always amazing to watch. This deep dive really shows that sometimes the biggest leaps forward come from questioning the things we thought were absolutely settled. Keep learning. Keep exploring that curiosity. We'll be back soon with another deep dive.